Hello everyone. In this question, we are asked to find the value of the sum of r going from 1 to n of the definite integral where theta goes from 0 to pi over 2 r plus sine theta whole square times cos theta of d theta. Okay, so this is a summation and a definite integral given together. And there are two variables here. The summation goes for r from 1 to n and the integral goes for theta from 0 to pi upon 2. Okay, so let us start the question. Okay, so we are given the summation of r goes from 1 to n, and this is going to be for theta. The definite integral is going to be for theta from 0 to pi over 2 r plus sine theta whole square times cos theta d theta. Okay, so for the definite integral, since we are taking the integral for the variable theta, r is a constant here. Okay, so if I take this, if I take let u be r plus sine theta, okay, then this will imply that du d theta, since r is a constant here, this will become cos theta, right? So on applying the chain rule of derivatives here, we can get du will be equal to cos theta d theta. Okay, this is not directly cross multiplication, this is from chain rule. Okay, so now we get the summation r goes from 1 to n. On changing this variable from theta to u, we have to change the limits also, right? So theta and u. Now theta was going from 0 to pi over 2. 0 to pi over 2, right? And if I put 0 in this equation here, we get u equal to r, right? Sine 0 is 0, so u equal to r. Then again, on putting theta equal to pi over 2, sine pi over 2 will become 1, so this will become u equal to r plus 1, right? So this integral now changes from theta equal to 0 to pi over 2 to u equal to r2 r plus 1, and this r plus sine theta whole square is equal to u square, right? And this remaining part cos theta d theta is equal to du. So this becomes a simple integral now, u square du. So this again, r goes from 1 to n. This will be u cube upon 3, u cube upon 3, where the limits are from r plus 1 to r, right? So this now becomes r goes from 1 to n. I can take the constant 1 by 3 out, and this will become equal to r plus 1 whole cube minus r cube, right? So if I take this constant out, this will become, if I open this bracket here, this will give me r cube plus 3r square plus 3r plus 1. This is r plus 1 whole cube, right? Minus r cube. So these two will get cancelled out. I am doing this in the rough. You can do it directly here also. Okay. So we are left with 3r square plus 3r plus 1. So now if I write this separately, this will become 1 by 3 times. This 3 will come out. Summation of r square as r goes from 1 to n plus 1 by 3 times summation r as r goes from 1 to n, and this will be summation of 1 n times, so this will be just n upon 3, right? So this and this will cancel out, this and this will cancel out, so summation r square as r goes from 1 to n, this is a simple formula, n into n plus 1 times 2n plus 1 upon 6. Similarly, summation r as r goes from 1 to n is n into n plus 1 upon 2, and the last term is n upon 3. So on taking the LCM here, we have 6 here. And, the first term, the numerator will remain as it is, and for the second term, the numerator will be multiplied by 3, 3n into n plus 1, and for the third term, the numerator will be multiplied by 2, so this is 2n. Okay, so in the numerator, n can be taken common here. So if I multiply these two terms, this will become 2n square plus 3n plus 1. Then here 3 will be taken inside this bracket, so this will become 3n plus 3, and here 2 will be left out, right, after taking n common, so 2 is left out. So this is the entire thing that is left inside the bracket. So this now becomes 2n square plus 3n plus 3n will become 6n, and 1 plus 3 plus 2 is 6 upon 6, right? So if I take 2 common out here, this will become 2n times n square plus 3n plus 3 upon 6, and on cancelling this 2 and 6, the final answer is n times n square plus 3n plus 3 in the numerator upon 3. Okay, so this is the required summation of the definite integral. Okay, so this is the answer given in the book also. Okay, so this is it. If you have any doubt, you can pause the video and see the step here. Okay, otherwise this is the required answer. Okay, so thank you for watching. Okay.